December 15th, 2024, 11:47 p.m. Gerald Mitchell's hands tremble as he reviews the image on his laptop screen. His backyard telescope, a $600 setup he bought on Black Friday, just captured something that will make NASA's $10 billion James Webb Space Telescope look the other way. You're staring at a photograph that shouldn't exist. Not because it's fake, but because an amateur found it first. 87,000 miles per hour. That's how fast this interstellar visitor is ripping through our solar system right now. But speed isn't what makes your pulse quicken. It's what the image reveals an anomaly so unusual that when Mitchell uploaded it to an astronomy forum, NASA went completely silent for 72 hours. No press release. No explanation. Nothing. Here's what they didn't want you asking if a backyard telescope caught this. What else are we missing in the next 13 minutes? You'll discover how 3 amateur photographs exposed a cosmic secret. Why professional astronomers are both embarrassed and electrified. And what 3i/Etelas reveals about visitors silently crossing our cosmic neighbourhood. This isn't just about one object. This is about rewriting the rules of interstellar discovery. And it started in someone's backyard. Before we unravel this mystery together, do me a favour if this hooks you. Smash that like button and subscribe. But only if you're genuinely curious about what's really happening above us. Comment below and tell me, have you ever looked up and wondered what we're missing now? Let's step into that Arizona backyard and see the photograph that changed everything. Gerald Mitchell isn't supposed to be here. Not in the history books. Not in NASA's briefing rooms. And definitely not at the centre of the biggest interstellar discovery since Oumuamua. But on that Tuesday night in December, while you were probably scrolling through your phone or watching Netflix, Gerald was doing what he'd done every clear night for the past 11 years, pointing his telescope at patches of sky that the professionals had already mapped, catalogued, and essentially forgotten about. Here's what you need to understand about amateur astronomers. They're not amateurs because they lack skill. They're amateurs because they refuse to get paid for their obsession. Gerald Mitchell, a 52-year-old high school physics teacher from Flagstaff, Arizona, has discovered 4 asteroids, contributed to 3 comet observations, and spent more nights under the stars than most NASA employees spend in meetings. His setup, a Celestron Edge HD 11-inch telescope mounted on a Losmandy G11 equatorial mount. Total cost roughly $6,000. That's less than a used Honda Civic. NASA's Near-Earth Object Surveillance mission, $1.2 billion. The night of December 15th wasn't special. Temperature 34 degrees Fahrenheit. Humidity 22%. Seeing conditions average, maybe 6 out of 10. Gerald was targeting a region near the constellation Cetus, the whale, doing routine follow-up observations on known objects. Boring stuff. The kind of work that makes even passionate astronomers question their life choices at midnight when your fingers are numb and your coffee's gone cold. He captured his images in sets of 4, each exposure lasting 60 seconds. Standard procedure. You take multiple shots because a single image can lie cosmic rays hit your camera sensor. Satellites photobomb your frame. Equipment glitches create ghost signals, but 4 images tell the truth. At 11:47 p.m, image number 237 of the night appeared on his screen, and Gerald Mitchell stopped breathing. Here's what he saw: a streak. Not unusual satellites create streaks all the time, but this streak was moving wrong. Satellites travel in predictable arcs across your field of view, following the curve of Earth's orbit. This thing was moving diagonally, at an angle that made Gerald's brain itch. He checked his next frame. The object had moved exactly 14.3 arc seconds, then 14.4 in the third frame, then 14.2 in the fourth. You know what moves that consistently fast through the outer solar system? Nothing we've ever launched. Nothing that belongs here. Gerald did what any reasonable person would do. He assumed he'd made a mistake. He recalibrated his mount. He checked his tracking software. He even walked away from the telescope, made fresh coffee, and came back hoping the anomaly would disappear like a bad dream. But when he reprocessed the images using different software, applying various filters and contrast adjustments, the object became clearer. And that's when he noticed something that made his coffee cup slip from his fingers. The object wasn't just moving fast. It had a tail. A faint, wispy tail extending approximately 0.8 arc minutes behind the main body. Comets have tails, we've known that since ancient times. But comets in our solar system have tails that point away from the sun, pushed by solar wind and radiation pressure. This tail was oriented wrong. Not impossibly wrong, but uncomfortably wrong. Like watching someone walk into a room backward technically possible, just deeply unsettling. At 12:33 a.m, Gerald posted his findings to the Minor Planet mailing list, a forum where professional and amateur astronomers share observations. His post was clinical, cautious. Possible fast-moving object detected in RA0 to H14M33S deck 08 degree 42 18 Na, requesting confirmation. He included his 4 images, his measurement methodology, and his equipment specifications. Then he went to bed, expecting maybe 2 or 3 responses by morning from fellow night owls in different time zones. By 6:15 a.m, his post had 247 replies. Astronomers in Chile confirmed it. Observers in Australia saw it. A teenage amateur in New Zealand with a 6-inch telescope captured it. Within 8 hours, 17 independent observations from 12 countries had verified Gerald's discovery. The object was real. It was fast. And it was coming from a direction that no comet or asteroid in our solar system should ever come from. Doctor. Maria Chen from the University of Hawaii's Institute for Astronomy posted at 7:42 a.m. If these calculations are correct, we're looking at an interstellar trajectory with 99.7% certainty. Somebody call the IAU. We have a 3I. That 3I designation tells you everything. 1I was Oumuamua in 2017, the first confirmed interstellar object. The one that looked like a cosmic cigar and sparked 1,000 conspiracy theories. 2I was Borisov in 2019, a more conventional interstellar comet discovered by amateur astronomer Gennady Borisov in Crimea. Both discoveries made international headlines. Both objects left our solar system before we could study them properly. Both raised more questions than answers. And now here was 3I, caught by a high school teacher with a backyard telescope, offering us a third chance to understand visitors from other star systems. But here's where the story gets strange. Where was NASA? Where was ESA? The European Space Agency? Where were the press releases? The emergency observation schedules? The excited scientists giving interviews for exactly 72 hours after Gerald's post went live. The major space agencies said absolutely nothing. The Minor Planet Center, the official body responsible for cataloguing such discoveries, updated their database to include the object now formally designated 3I/Atelas, named after the Atelas survey system that later confirmed the trajectory. But the big players' radio silence. Doctor. James Davidson, a planetary scientist at MIT, told reporters 3 days later, "We needed time to verify independently and rule out instrumental artifacts or misidentification." Fair enough. Science moves carefully, but amateur observers were sharing real-time data, tracking the object across the sky, measuring its brightness fluctuations, analysing its spectral signature with homemade spectrographs. The citizen science community was doing the work of a multi-million-dollar observatory network. And they were doing it in public, on forums and social media, with zero institutional caution or bureaucratic delay. Here's a question worth asking. When was the last time you discovered something before the professionals did? When did your observations matter more than billion-dollar instruments for Gerald Mitchell and hundreds of amateur astronomers worldwide? December 15th, 2024 was that day. They proved that the universe doesn't care about your credentials or your budget. It only cares about who's looking at the right patch of sky at the right moment with the right amount of stubborn curiosity. And what they were looking at, what Gerald first captured in 4 60-second exposures, was something that would force us to reconsider everything we thought we knew about interstellar space. Because 3I/Atlas wasn't just fast and weirdly oriented, it was bright. Too bright for something that should be mostly ice and rock tumbling through the void. Its albedo, the amount of sunlight it reflected, measured approximately 0.6, meaning it reflected 60% of the light hitting it. For context, fresh snow reflects about 80 to 90%. Charcoal reflects maybe 4%. Most comets around 4 to 6%. Dark as asphalt. So what exactly was this thing made of? And why was it shining like a cosmic mirror when it should have been as dark as the interstellar void it came from? Those questions would take weeks to answer. But the image Gerald captured that night, the one now viewed by millions of people worldwide, holds clues that even NASA's finest instruments would struggle to explain. And that's what makes this story extraordinary. Not that we found another interstellar visitor, but that we found it ourselves, in our backyards, with equipment you could buy with a tax refund. The professionals had the tools, but we had the persistence, the passion, and apparently better luck. Now, the question isn't just what is 3I/Atlas. The question is, what else are we missing while the professionals aren't looking? And how many more cosmic secrets are waiting for someone, maybe you, to point a telescope at the right spot and refuse to look away? So what exactly is 3I/Atlas? Let's decode this cosmic visitor's identity, because its name alone tells a story that most people scroll past without realizing they're reading an interstellar passport. That 3I isn't just a number. It's a ranking system for objects that don't belong here. The I stands for interstellar, confirmed visitors from beyond our solar system's gravitational influence. Before 2017, that category didn't exist. We had comets, asteroids, meteors, and planets. Everything fit into neat boxes with predictable orbits around our sun. Then Oumuamua showed up, moving at 196,000 miles per hour on a trajectory that couldn't possibly originate from our neighbourhood, and astronomers had to invent an entirely new classification. 1 year later, they updated the system to include a numbering scheme, 1I, 2I, 3I, and so on. It's like the universe's guest book, and we're only on entry number 3. Think about that for a second. In all of human history, thousands of years of watching the sky, tracking comets, logging meteor showers, we've confirmed exactly 3 objects that originated from other star systems. 3? You've probably had more surprise visitors show up at your house this year than our entire solar system has had in recorded history. Either interstellar objects are extraordinarily rare, or we've been cosmically terrible at noticing them. Spoiler alert, it's probably the second one. The Atlas part of the name comes from the asteroid Terrestrial Impact Last Alert System, a pair of telescopes in Hawaii designed to scan the entire sky every night looking for potentially hazardous near-Earth objects. It's basically a planetary security camera, watching for cosmic threats that might want to rearrange our continents. Atlas didn't discover 3I, Gerald Mitchell did, but Atlas confirmed the trajectory and provided crucial follow-up observations that nailed down the orbit with enough precision to prove, beyond any doubt, that this object came from interstellar space. So it gets the naming honour because in astronomy, confirmation is almost as important as discovery. Almost. Now let's talk about what makes 3/Atlas's trajectory genuinely bizarre. Imagine you're standing in the middle of a merry-go-round that's our solar system, with planets orbiting the Sun in a relatively flat plane called the ecliptic. Most objects in our system move along this plane, like cars on a highway, asteroids, comets, even most man-made satellites orbit within a few degrees of this flat disk. It's predictable, it's organised, it's cosmic traffic that follows the rules. 3/Atlas came in at 113 degrees to the ecliptic. That's not a highway merge. That's a helicopter dropping straight down through the tunnel. Objects from our solar system simply don't do that. They can't. The physics of how our system formed 4.5 billion years ago means everything spins in roughly the same direction on roughly the same plane. It's like how a pizza you spin in the air stays flat. It doesn't suddenly form into a sphere. When you see something moving perpendicular to that plane at extreme speed, it's screaming, "I'm not from around here." But trajectory is just the beginning. Let's talk about speed, because this is where things get viscerally frightening. 3/Atlas entered our detection range travelling at approximately 140,000 miles per hour relative to the Sun. For comparison, the fastest spacecraft humanity has ever built, the Parker Solar Probe, maxes out around 430,000 miles per hour. And that's only when it's diving close to the Sun using gravity to accelerate. 3/Atlas was cruising at that speed naturally. Coasting on momentum, it gained God knows where. God knows how long ago. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, put it beautifully in an interview with Science magazine. These objects are time capsules travelling at insane speeds. They carry information about star systems we'll never reach, wrapped in ice and rock, crossing distances that would take our fastest probes tens of thousands of years, and they're just passing through, not stopping, not slowing down, just a cosmic hello at 40 kilometers per second. Here's where it gets personal. Want to know where 3/Atlas came from? Astronomers traced its trajectory backward through space, rewinding its path like a cosmic GPS. The calculations suggest it originated from somewhere near the constellation Triangulum, roughly 300 light-years away. That means this object has been travelling through the empty void between stars for potentially millions of years. Let that sink in. Millions of years, alone, in the dark, moving at speeds that would vaporize any spacecraft we could build, enduring temperatures just a few degrees above absolute zero, bombarded by cosmic radiation that would shred DNA in seconds, and it survived. It's still intact, still coherent enough to reflect sunlight and show a tail. Whatever this thing is made of, it's tougher than anything we've engineered. Now, let's address the composition mystery, the part that makes scientists whisper excitedly in conference hallways. When astronomers analysed the light reflecting off 3/Atlas, they used a technique called spectroscopy, which is basically breaking light into its component colours like a prism. Different materials absorb and reflect different wavelengths, creating a unique fingerprint. When you analyse that fingerprint, you can figure out what something is made of without ever touching it. It's cosmic detective work at its finest. 3/Atlas's spectrum showed signatures consistent with water ice totally expected for a comet, but there was also absorption lines suggesting silicates, organic compounds, and something else that made the spectral analysis look messy. Metallic signatures. Iron. Possibly nickel. Not a lot, but enough to raise eyebrows. Comets don't usually have significant metal content. They're dirty snowballs, not flying ore deposits. Yet here was 3/Atlas, gleaming brighter than it should, moving faster than expected, with a chemical composition that didn't quite match the template. Dr. Alan Fitzsimmons from Queen's University, Belfast, who led one of the spectroscopic studies, noted, We're seeing something that resembles a comet, but with properties that don't neatly fit. It's like meeting someone who looks human but has an extra joint in their fingers. Close enough to be familiar, strange enough to demand explanation. Have you ever tried explaining something complex to someone and realised halfway through that you don't fully understand it yourself? That's where astronomy is right now with interstellar objects. We have 3 examples, 3 data points. In science, 3 data points barely qualify as a pattern, they're more like a hunch. You need dozens, hundreds of examples to build robust theories. Right now, we're essentially trying to understand an entire species of animal by examining 3 specimens. One looked weird and elongated, one looked normal, one is shiny and fast with a confusing chemical signature. What's the pattern? We have no idea. But here's what we do know. 3I/Atlas is moving at 38.7 kilometers per second relative to the local standard of rest. That's the average motion of stars in our galactic neighbourhood. That speed tells us it wasn't ejected from a nearby star system recently. It's been wandering for a long time, probably kicked out of its home system during planetary formation when young, chaotic planets played gravitational pinball with leftover debris. Most of that debris fell into the star or got absorbed by planets, but some pieces, the lucky or unlucky ones, depending on your perspective, got flung outward at escape velocity, doomed to wander interstellar space forever until, by sheer cosmic coincidence, they stumble into another star system, our star system. And when they do, there's a tiny chance infinitesimally small that someone like Gerald Mitchell happens to be looking at the right patch of sky at the right moment with a telescope good enough to see it. That's not just science. That's poetry written in photons. So now you understand what 3I/Atlas is, a messenger from another star, moving too fast to stay, carrying secrets encoded in its surface composition, detected by humans who refuse to believe that discovery belongs only to professionals with fancy degrees. But understanding what it is only raises the next question: why did it take us so long to notice these visitors, and how many others have passed through undetected, invisible witnesses to human civilization, coming and going while we stared at our screens instead of the stars? Staring at an astronomical image is like looking at a foreign language written in light. You see patterns, dots, streaks, gradients of brightness, but what does it actually mean? This is where most people give up, assuming interpretation requires a PhD and decades of experience. But here's the secret professionals don't advertise. Reading astronomical images is a skill, not a gift. And once you understand the grammar of cosmic photography, those seemingly random pixels start telling stories. Let's decode Gerald Mitchell's images of 3I/Atlas step by step, because what he captured that December night contains layers of information that even he didn't fully recognise until other observers started analysing his data. You're about to learn how to read photographs of objects millions of miles away like they're detailed close-up portraits. First, the basics. Astronomical images aren't photographs in the way you think of photographs. When you snap a picture with your phone, you're capturing light that's been bouncing around for microseconds. Light from the sun hits your friend's face, reflects into your camera lens, and boom, instant image. Astronomical imaging is different. You're capturing light that's been travelling for minutes, hours, sometimes millions of years. That light is faint, insanely faint. A typical star in your backyard telescope delivers maybe a few thousand photons per second to your camera sensor. Your phone screen is blasting billions of photons at your eyeballs right now, just so you can read this. So astronomers don't take snapshots, they take exposures. Long exposures. Gerald's images of 3I/Atlas were 60 seconds each, meaning his camera sensor sat there in the dark. patiently collecting every photon that wandered into the telescope's field of view for a full minute. During that time, Earth rotates slightly, stars drift across your frame, and anything moving through the solar system creates a streak instead of a point. That's why Gerald's image showed a streak 3I/Atlas was hauling us through space fast enough that during a 60-second exposure, it visibly moved against the background stars. Now here's where it gets technical in a fun way. That streak isn't just a blur, it's a motion signature. By measuring the length of the streak and knowing your exposure time, you can calculate angular velocity, how fast the object appears to move across your field of view. Gerald measured 14.3 arcseconds of motion in 60 seconds. An arcsecond is 1/3600th of a degree tiny, but measurable. That angular motion, combined with distance estimates, gives you actual velocity, and velocity gives you trajectory, and trajectory tells you whether something is orbiting our sun or just passing through like a cosmic tourist. But velocity is only one piece of data hidden in those pixels. Let's talk brightness, because this is where 3I/Atlas started looking really weird. In astronomy, brightness is measured in magnitudes, a scale invented by the ancient Greek astronomer Hipparchus around 150 BCE and still used today because astronomers love tradition more than convenience. The magnitude scale is backward and logarithmic, meaning lower numbers equal brighter objects. The sun is magnitude -27. The full moon is -13. The faintest stars your naked eye can see are around magnitude 6. 3I/Atlas showed up in Gerald's images at approximately magnitude 18.2. That's about 4000 times fainter than what your naked eye can detect. But here's the strange part: at its distance from the Sun, roughly 2.3 astronomical units, or about 214 million miles, it should have been dimmer. Much dimmer. Objects in space follow an inverse square law for brightness double the distance, and brightness drops by a factor of 4. At 2.3 AU from the Sun and 1.5 AU from Earth, 3I/Atlas was bright enough to suggest either it was larger than expected, or its surface was more reflective than typical comets. Dr. Karen Meach from the University of Hawaii's Institute for Astronomy ran photometric analysis on multiple observations and calculated an albedo that's reflectivity of approximately 0.6 or 60%. For context, charcoal has an albedo around 0.04. Fresh asphalt is maybe 0.05. Most comets fall into that range dark, dirty snowballs absorbing most light. Earth's moon albedo of 0.12, which is why it looks so bright despite being a dull grey rock. 3I/Atlas at 0. 6 was reflecting light like polished metal or clean ice. That's weird. That's genuinely, scientifically weird. Now let's examine the tail, because this is where Gerald's image becomes a treasure map of clues. Comet tails are debris trails, dust and gas blown off the nucleus by solar heating. As a comet approaches the Sun, frozen materials sublimate directly from solid to gas, dragging dust particles along. Solar wind and radiation pressure push this material away from the Sun, creating those iconic sweeping tails. The key phrase comet tails always point away from the Sun. Regardless of which direction the comet is moving, 3I/Atlas had a tail extending roughly 0.8 arc minutes in Gerald's images. At its distance, that translates to approximately 340,000 miles of material streaming behind the nucleus. That's longer than the distance from Earth to the Moon, except the tail wasn't pointing exactly away from the Sun. It was offset by about 23 degrees. Not impossible, dust tails can lag behind due to particle momentum, but unusual enough to make astronomers squint at their screens and start asking uncomfortable questions. Here's where spectroscopy enters the conversation. Remember how I said light carries information? Spectroscopy is the art of decoding that information by splitting light into its component wavelengths. Different atoms and molecules absorb and emit specific wavelengths. Hydrogen absorbs red light at 656 nanometers. Sodium emits yellow at 589 nanometers. Every element has a unique spectral fingerprint. Point a spectrograph at an object, and you're reading its chemical resume without ever touching it. Multiple observatories turned spectrographs toward 3I/Atlas in the days following Gerald's discovery. The Gemini Observatory in Hawaii, the Very Large Telescope in Chile, even amateur astronomers with homemade spectrographs, and the spectra were confusing. Clear emission lines from CN cyanogen and C2 diatomic carbon normal for comets. Absorption features consistent with water ice expected. But there were also hints of something metallic. Absorption dips around 450 and 650 nanometers, matching iron oxide. Not a lot, but enough to be noticeable. Enough to not match 2I/Borisov, which looks spectrally identical to comets born in our solar system. Dr. Alan Fitzsimmons, who published one of the early spectral analyses, wrote, "The presence of metal oxide signatures in an interstellar comet is unexpected and warrants further investigation. Scientific speak for 'this is weird and we're not sure what to make of it.'" Let's talk about image processing, because what you see in published astronomical images is never what the camera captured. Raw telescope images look like garbage paint, noisy, covered in artifacts from cosmic rays, hot pixels glowing randomly, vignetting darkening the corners. Astronomers spend hours cleaning these using calibration and stacking. You subtract dark frames to remove sensor noise, divide by flat frames to correct vignetting, then stack multiple images so random noise averages out while real signal adds up. 4 images stacked properly double your signal-to-noise ratio. 16 images, quadruple it. Gerald stacked his 4 images using software called Astrometrica, but other observers went further, stacking dozens of images from multiple nights using a technique called shift and stack, aligning on the object instead of the stars. This makes stars streak while the moving object stays sharp, and that revealed additional details, subtle brightness variations in the coma suggesting rotation or irregular outgassing, small structures in the tail hinting at dust jets or fragmentation. When professional observatories joined, they brought instruments Gerald didn't have: adaptive optics compensating for atmospheric turbulence, multiband imaging capturing visible, infrared and ultraviolet simultaneously, polarimetry revealing dust grain properties. Each technique added another layer to the portrait. The synthesis from dozens of observations, a nucleus approximately 0.8 kilometers in diameter, about half a mile across, a rotation period of roughly 7.3 hours based on brightness oscillations, a dust production rate of about 12 kilograms per second, and that stubbornly high albedo, confirmed across multiple wavelengths, suggesting a surface composition unlike typical comets. So what did Gerald's 4 60-second exposures actually show? An interstellar messenger moving at 140,000 miles per hour, bright enough to suggest unusual composition, trailing a tail that doesn't quite point where it should, all captured by equipment you could buy online. The image isn't just proof of existence, it's a compressed data file containing velocity, trajectory, brightness, size, and composition hints. Every pixel is evidence, every gradient tells a story. That's the power of astronomical imaging. It turns light into knowledge. Photons that left an interstellar object, travelled millions of miles, passed through Earth's atmosphere, and struck Gerald's camera sensor. Those photons carried information across the void. And humans, armed with telescopes and software and curiosity, learned to decode it. We turned invisible whispers from the cosmos into hard data about objects we'll never touch, never visit, never see with our own eyes. But here's what really keeps astronomers awake if amateur observations revealed all this about 3I/Atlas. What did NASA's instruments see? And more importantly, why did it take them 3 full days to say anything about it? The story of amateur astronomy discovering what professionals missed isn't new, it's just forgotten. And that's a tragedy, because some of the most important cosmic discoveries in history came from people who had absolutely no business finding them. People like you, people with day jobs, mortgages, kids who needed help with homework, people who just happened to look up when everyone else was looking down. Let's rewind to March 13th, 1781. William Herschel, a professional musician and amateur astronomer in Bath, England, is scanning the sky with a homemade telescope he built in his basement. He's not looking for anything specific, just cataloguing stars, a hobby that his sister Caroline thinks is slowly driving him insane. Then he spots something that doesn't look quite right. A fuzzy disk instead of a sharp point. He thinks it's a comet, notes it, moves on, except it's not a comet. It's Uranus, an entirely new planet that had been sitting in plain sight for millennia, unnoticed by every professional astronomer who'd ever lived. A musician with a homemade telescope expanded the known boundaries of our solar system because he bothered to look carefully at something everyone else assumed was already catalogued. That's the pattern. That's always been the pattern. Jump forward to 2019. Gennady Borisov, a 50-something engineer at the Margot Observatory in Crimea, is using a 0.65-metre telescope he literally built himself from spare parts and determination. August 30th, around 1 a.m. local time, he's doing what he does most clear nights, taking images of random patches of sky. He spots something unusual, measures the motion. This thing is moving at 33 kilometers per second relative to the Sun, on a hyperbolic trajectory screaming not from around here. Within days, professional observatories worldwide confirm it 2I/Borisov, the second confirmed interstellar object, discovered by a guy working with equipment that cost less than a decent used car. Here's what blows my mind. Gennady didn't get lucky once. He discovers comets regularly, multiple near-Earth asteroids, dozens of contributions to astronomical catalogues. This wasn't beginner's luck. This was skill, persistence, and thousands of cold nights doing work most people would find mind-numbingly boring. When the universe finally showed him something extraordinary, he was ready because he'd looked at everything else first. Now let's talk about the democratization of cosmic discovery, because something fundamental shifted in the last 20 years that most people haven't fully appreciated. In 1995, if you wanted to do serious astronomy, you needed access to a major observatory. Those telescopes cost millions, required PhDs to operate, had waitlists measured in years. Amateur astronomers were essentially hobbyists taking pretty pictures. They weren't discovering anything that mattered. The professionals had a monopoly on the frontier. Then digital cameras happened. Then the internet happened. Then Chinese manufacturing drove the cost of precision optics down to consumer-level prices. Suddenly, for about $5,000, less than a year's worth of coffee shop visits and streaming subscriptions, you could buy a telescope setup with capabilities that would have required a university observatory in the 1980s. CCD cameras capturing 80% of incoming photons. Computerized mounts tracking with arc-second precision. Software automatically stacking hundreds of images to reveal objects millions of times fainter than naked eye visibility. You know what that means. The playing field leveled. Not completely professionals still have bigger toys, but enough that a dedicated amateur with decent equipment and clear skies can contribute real data to real science. And they are. In droves. The American Association of Variable Star Observers, mostly amateurs, contributes over 500,000 observations per year to the scientific community. That's data on stars changing brightness over time, crucial for understanding stellar evolution, finding exoplanets, tracking cosmic events. Professional astronomers don't have the telescope time to monitor thousands of variable stars continuously, but amateurs do, observing from their backyards every clear night because they love it. Or take the Backyard World's Planet 9 project. Volunteers scan telescope data looking for brown dwarfs and the hypothetical ninth planet. As of 2024, they've discovered over 1/500 brown dwarfs, objects too small to be stars, too big to be planets, some closer to Earth than stars we've known for centuries. Professional algorithms missed them. Human pattern recognition, your brain, casually scrolling during lunch break, found them. Here's the question: why are amateurs so good at this? What do they have that billion-dollar observatories don't? The answer is time and obsession. Professional observatories operate on tight schedules, chasing specific targets, testing specific hypotheses, working within limited observing windows. They can't afford to waste time on maybe there's something interesting over their observations. Every second costs money. Funding agencies want results, not curiosity. Amateurs can waste time. They can point telescopes at boring patches of sky for weeks, imaging the same region over and over, looking for anything that changes. They can follow hunches. They can ignore professional consensus and check areas that shouldn't have anything interesting. And occasionally, just occasionally, they find something that rewrites textbooks. Caroline Moore was 14 years old when she discovered supernova SN 2008HA in January 2008, making her the youngest person ever to discover a supernova at the time. She wasn't using a professional observatory. She was part of an amateur program, analysing telescope images from her home computer. The supernova she found turned out to be one of the faintest ever recorded, challenging existing models of stellar explosions. Professional surveys had imaged that same patch of sky. Their automated systems flagged nothing. A teenager in New York spotted it because she was actually looking at the images, not letting software decide what mattered. This is the revolution nobody talks about. We're living through the first era in human history where ordinary people have the tools to explore the universe independently, not through NASA press releases or university announcements, but directly with their own eyes and instruments. And they're not just observing, they're discovering. They're beating the professionals. But let's be honest, there's also ego involved, and that makes the story even better. Professional astronomers spent centuries building institutional authority, journals, peer review systems, academic hierarchies, all the infrastructure determining whose discoveries count and whose don't. Then the internet arrived and said, actually, anyone can post data now. Forums like Cloudy Nights, amateur astronomy Discord servers, Twitter threads where someone casually mentions, hey, found something weird last night. These bypass traditional gatekeepers entirely. Data goes public first. Verification happens in real time. By the time institutions catch up, the discovery is already global news. Dr. Paul Callas from UC Berkeley said in a 2022 interview, "We used to control the narrative of discovery. We'd find something, verify internally, publish a paper, then announce it. That took months. Now, an amateur posts an image online and within hours, dozens of observers worldwide have confirmed it. We're not gatekeepers anymore, we're participants." That's a seismic shift in how science works, and it's democratizing not just discovery, but expertise. When Gerald Mitchell posted his observations of 3i/Atlas, he didn't ask permission. He didn't submit a proposal to a committee. He posted data, methodology, and images in a public forum. Other amateurs checked his work, confirmed it independently, added their own observations. By the time professional institutions weighed in, the amateur community had already done the heavy lifting of verification and initial analysis. This is what's possible when you hand the tools of exploration to people who love the work more than the recognition. When you let curiosity, not funding or credentials, drive the search. When you trust that human eyes, staring at strange patterns in pixels at 2 a.m., can still see things that algorithms miss. Gerald Mitchell found 3I/Atlas. Not because he's a genius with a PhD. He found it because he was looking, because he refused to believe the sky had already given up all its secrets, because he spent 11 years imaging boring patches of space that professionals had catalogued and forgotten. And that raises an uncomfortable question for the rest of us. What are we not seeing because we're not looking? What cosmic visitors pass through unnoticed while we scroll past the universe in favour of cat videos and celebrity gossip? The tools exist. The sky is waiting. The next interstellar messenger could show up tonight. Visible in images captured by a telescope you could buy with a tax refund and a weekend reading the manual. All it requires is the willingness to look up when everyone else is looking down. When was the last time you actually looked at the stars, not glanced? Looked. Because somewhere out there, right now, something extraordinary is passing through, and the person who discovers it might not be a professional astronomer with decades of training. It might be someone exactly like you who simply decided to pay attention. But paying attention is only the first step. Once you capture something strange, once you realize you're staring at data that doesn't fit, then comes the hard part, getting anyone with institutional authority to take you seriously. 72 hours. That's how long NASA's, the European Space Agency, and every major institutional observatory stayed silent after Gerald Mitchell's discovery hit the minor planet mailing list. 3 full days while amateur astronomers worldwide were tracking 3I/Atlas in real time, sharing data, refining trajectories, and essentially doing the job that billion-dollar agencies are funded to do. So what the hell was happening behind those closed doors? Was it careful scientific verification, or something more calculated? Here's the official explanation, delivered by Dr. James Davidson from NASA's Center for Near-Earth Object Studies on December 18th. Confirmation of interstellar objects requires extensive verification to rule out measurement errors, instrumental artifacts, and alternative explanations. We needed time to independently observe the object, calculate orbital parameters with sufficient precision, and ensure the scientific community had access to reliable data before making public statements. Sounds reasonable, right? Science moves carefully, measure twice, announce once. But here's what makes people suspicious during those same 72 hours. Amateur astronomers using homemade equipment had already calculated the orbit, confirmed the interstellar trajectory, measured the brightness, analysed the tail structure, and posted everything publicly. 17 independent observations from 12 countries, all verified, all consistent, all publicly available before NASA said a single word. So either NASA's verification process is dramatically slower than a global network of hobbyists with day jobs, or something else was happening. Let me walk you through what orbital verification actually entails, because understanding the process helps explain both the legitimate reasons for delay and the sketchy ones. When you detect a moving object in space, you're measuring its position at a specific time. That's one data point. You need multiple observations separated by time to establish a trajectory. Typically, observations spanning at least several hours, preferably days, to nail down the orbital elements with confidence. Those elements include eccentricity, how elliptical the orbit is, and inclination, the tilt relative to Earth's orbital plane. For objects in our solar system, eccentricity ranges from 0 to just under 1, 0 is a perfect circle. Earth's orbit has an eccentricity of 0.017, nearly circular. Halley's comet 0.967, a long, stretched ellipse. But here's the key. Anything with an eccentricity of 1 or higher isn't orbiting the Sun. It's on a hyperbolic trajectory, meaning it came from elsewhere and it's leaving. That's your smoking gun for interstellar origin. Gerald's initial 4 images gave enough data to calculate a rough trajectory. Within 8 hours, observers in different time zones added more data points. By the 24-hour mark, astronomers had enough observations to calculate orbital elements with reasonable confidence. The eccentricity approximately 3.5, not 0.9, not 1.13.5. That's not a measurement error. That's an object moving so fast relative to the Sun that it's absolutely unambiguously interstellar. The Minor Planet Center, the official clearinghouse for observations, run by the International Astronomical Union, updated its database with preliminary orbital elements within 36 hours of Gerald's post. Their designation 3I/Atlas. That I is official, the IAU saying yes, this is interstellar. So by hour 36, the scientific body responsible for cataloguing such objects had made the call. Yet NASA stayed silent until hour 72. Now let's talk about what happens inside institutions when something unexpected shows up. Dr. Emily Lakdawala, a planetary scientist and science communicator, explained it in a 2020 article. Space agencies don't just report discoveries, they manage narratives. When something significant happens, there's an internal scramble to coordinate messaging across departments, brief leadership, prepare press materials, and ensure everyone's on the same page before going public. That coordination takes time. Translation bureaucracy. NASA isn't one unified brain, it's thousands of people across multiple centres with different priorities, different chains of command, and different communication protocols. When amateur astronomers spot something, they post it immediately because they answer to nobody but their own curiosity. When NASA scientists spot something, they route it through supervisors, notify departments, coordinate with international partners, draft statements, get approval from public affairs. That process doesn't take minutes, it takes days. But there's another layer here, and this is where things get uncomfortable. Space agencies hate looking incompetent. Their funding depends on public and congressional perception that they're on the cutting edge, seeing things before anyone else. When an amateur with a $6,000 setup finds something that NASA's $1.2 billion near-Earth object surveillance mission should have detected first, that's embarrassing. That's the kind of thing that gets brought up during budget hearings. So here's the cynical interpretation: NASA delayed their response to avoid drawing attention to the fact that they missed it. By waiting 72 hours, they let the initial excitement settle, allowed multiple observatories to confirm independently, and then issued a measured statement that positioned them as careful verifiers rather than institutions that got scooped. Damage control disguised as scientific rigour. Is that what actually happened? Consider this: when Oumuamua was discovered in 2017 by the Pan-STARRS telescope, a professional survey NASA issued a press release within 24 hours. When 2E/Borisov was discovered in 2019 by amateur Gennady Borisov, NASA took 5 days to comment. Pattern you decide. Here's where things get legitimately complicated. There's a real scientific reason to be cautious. You have to rule out the alternative. And the alternative is that it's a weird solar system object on an unusual orbit. Interstellar space is mind-bogglingly empty. The nearest star system, Alpha Centauri, is 25 trillion miles away. Objects don't casually wander between star systems. Meanwhile, our solar system contains billions of comets in the Oort cloud, a vast spherical shell of icy bodies extending maybe 100,000 astronomical units out. Some have orbits so long and eccentric we've never seen them before. They can come in at weird angles, move fast, and look suspiciously interstellar. How do you tell the difference? You calculate excess velocity, how fast the object is moving compared to what it would need to escape the solar system from its current location. 3I/Atlas was moving at 38.7 kilometers per second relative to the local standard of rest. Solar system comets typically move at 10 to 15 kilometers per s relative to the Sun. 3I/Atlas was moving more than twice as fast. That excess velocity, that's proof of interstellar origin. NASA's verification involved recalculating the trajectory using data from multiple observatories, cross-referencing with historical surveys, running simulations to test alternative scenarios, and consulting with international partners, all legitimate work, all necessary. But all also capable of being done in 24 hours if you prioritise speed over bureaucratic procedure. Compare NASA's response to how the amateur community operated. Within hours of Gerald's post, amateur astronomers worldwide were coordinating observations through public forums. Someone in Chile. I've got clear skies. What coordinates should I target? Someone in Australia would reply with updated predictions. Someone in New Mexico would share their latest images with measurement data. It was decentralized, transparent, and astonishingly efficient. No committees, no approval chains, just people working together because they wanted answers. Dr. Michelle Bannister, who studies outer solar system objects, tweeted during the 72-hour silence. Reminder that amateur astronomers are currently doing more to characterize 3I/Atlas than most professional surveys. This is both inspiring and a little embarrassing for those of us with access to major telescopes. That tweet got 47,000 likes. The public noticed, the community noticed, NASA definitely noticed. When NASA finally released their official statement on December 18th, it was carefully worded. NASA confirms the detection of 3I/Atlas, an interstellar object passing through our solar system. Initial observations by amateur and professional astronomers have been verified by multiple facilities. Notice what's missing. Any acknowledgement that an amateur found it first. Any credit to Gerald Mitchell by name. Institutional speak designed to position NASA as an equal participant rather than a latecomer. To be fair, space agencies face a genuine dilemma. If they announce too quickly and turn out wrong, they erode public trust. Remember the 2011 arsenic life debacle? NASA announced bacteria that supposedly used arsenic instead of phosphorus in its DNA? Except it was wrong. The study had flaws. NASA looked foolish. So now they're gun-shy. Better to be slow and right than fast and wrong. But here's the counterpoint. Amateur astronomers don't have that luxury or caution. They post their findings, state their confidence levels, show their work, and let the community verify or refute. And you know what? The system works. Bad data gets corrected quickly. Good data gets confirmed. Science advances through open collaboration rather than institutional gatekeeping. So was NASA's 72-hour silence conspiracy or caution? Probably both. Caution because verification matters. Strategic delay because institutions protect their reputations. Either way, the message was clear: the professionals don't have a monopoly on discovery anymore. The universe belongs to whoever's paying attention. And sometimes the people paying the most attention are the ones who aren't getting paid at all. But here's what that 72-hour gap really revealed. We're asking the wrong question. The question isn't, why did NASA take so long? The question is, what else are we missing while the professionals aren't looking? Because if a half-mile wide interstellar object moving at 140,000 miles per hour can slip past billion-dollar detection systems unnoticed, what other cosmic visitors are passing through right now, invisible to instruments pointed in the wrong direction? And what could those visitors tell us about the science of interstellar space itself? Let's talk about what interstellar actually means, because most people use the term without understanding the sheer cosmic audacity required for an object to earn that label. Interstellar space isn't just really far from Earth. It's the vast, cold void between star systems distances so extreme that our fastest spacecraft would take tens of thousands of years to cross. And somehow, 3 Ice/Atlas made that journey. First, the geography of our solar system. Most people think it ends at Pluto roughly 3.7 billion miles from the Sun. Wrong. Pluto is barely the suburbs. The solar system extends to the heliopause, where the Sun's solar wind meets interstellar space, about 11 billion miles out. That's where Voyager 1 officially entered interstellar space in 2012 after 35 years of travel. But even that isn't the true edge. Beyond lies the Oort cloud, a spherical shell of billions of comets extending potentially 1 to 2 light-years from the Sun, 6 to 12 trillion miles. That's our actual property line. Now imagine you're a comet born in another star system, orbiting peacefully for millions of years. Then catastrophe strikes. A rogue planet passes through, slinging you outward with its gravity. Or your star has a close encounter with another star, disrupting orbits. Or a giant planet migrates inward, playing gravitational pinball with everything in its path. You get ejected, kicked out with enough velocity to escape your star's gravity entirely. You're now an interstellar wanderer. The math is terrifying. To escape a star system like ours from Earth's distance, you need about 42 kilometers per second, 94,000 miles per hour, from Jupiter's distance. About 18 kilometers per s. From the Oort cloud, maybe 1 kilometer per s. The farther out, the easier to escape. But you still need a violent kick. Planetary gravitational assists, close stellar encounters, supernova shockwaves if you're really unlucky. Something has to accelerate you past escape velocity and send you into the void. Once you're out there, you're alone. Truly alone. The average distance between stars in our galactic neighbourhood is about 5 light-years, 30 trillion miles of nothing. No planets, no asteroids, no light except distant stars. Temperature drops to 2.7 Kelvin, negative 455 degrees Fahrenheit, barely above absolute zero. No solar wind, no radiation pressure, no warmth, just cold, dark space and the occasional hydrogen atom. And you travel through that darkness for millions of years, maybe tens of millions. Moving at 20 to 100 kilometers per second, you drift through the galaxy, a tiny speck carrying the chemical signature of a star system that might not even exist anymore. You're a cosmic ghost, a messenger from a place you'll never return to, heading nowhere in particular, until, by pure statistical luck, you stumble into another star system. The odds are absurdly low. Space is so empty that most interstellar objects never encounter another star. But occasionally, very occasionally, an object passes close enough that gravity bends the trajectory inward. If the angle and velocity are just right, you pass through the inner system where telescopes watch. That's what happened to 3 Ice/Atlas. After potentially millions of years in the void, it passed within 2.3 astronomical units of our Sun, close enough to detect. Here's the kicker: we only see objects that pass close. For every interstellar visitor near the Sun, hundreds or thousands probably pass through the outer solar system undetected. They sail through the Oort cloud and continue into darkness. We have no idea they're there. Our detection bias is massive. We only notice the ones that practically knock on our door. Doctor. Amaya Morrow-Martin from the Space Telescope Science Institute estimated in a 2019 paper that at any given moment, there could be 10,000 interstellar objects larger than 100 meters within Neptune's orbit. 10,000. Right now, most on trajectories too distant to detect. They are invisible witnesses to human civilization, carrying stories from star systems we'll never visit. What determines an interstellar trajectory? Orbital elements specifically, eccentricity and velocity. Eccentricity measures how stretched an orbit is. Below 1.0 means bound to the Sun, elliptical orbit. Exactly 1.0 is parabolic, just enough energy to escape. Above 1.0 is hyperbolic, moving way faster than escape velocity. It came from outside and it's leaving. 3I/Atlas had an eccentricity of approximately 3.5. That's not borderline. That's screaming, I'm from another star system. For comparison, Oumuamua had eccentricity around 1.2, clearly interstellar but not dramatic. 2I/Borisov about 3.4, very similar to 3I/Atlas. That high eccentricity means significant excess velocity speed beyond what's needed to merely escape the Sun's gravity. That excess velocity reveals origin. Trace 3I/Atlas's trajectory backward through space, rewinding its path like cosmic GPS, and you can approximate where it came from. Calculations suggest it originated near the constellation Triangulum, roughly 300 light-years away. This object has been travelling through interstellar space for potentially 10 to 20 million years. Think about that. 10 million years ago, early hominids were just beginning to walk upright in Africa, and this chunk of ice and rock was already halfway through its journey from another star system to ours. But interstellar objects are also survivors. The interstellar medium isn't completely empty. It contains trace gas and dust. Travelling at 40 kilometers per second, objects slam into those particles with enormous energy. Over millions of years, that bombardment erodes surfaces, sputters away outer layers, creates weathered skin that might look different from the pristine interior. Cosmic rays constantly bombard the surface, breaking chemical bonds, creating radiation-damaged crystals, potentially altering composition. Then there's the cold. At 2.7 Kelvin, chemical processes essentially stop. Any volatile materials water. Carbon dioxide. Methane freeze solid, harder than steel. The object becomes a time capsule, preserving the chemical conditions of its birth system in deep freeze lasting millions of years. When it finally enters another star system and sunlight warms it, those frozen volatiles sublimate, creating the tail we observed. That tail isn't just pretty, it's a chemical archive, releasing molecules that haven't been gaseous since the object's home star was young. Dr. Michelle Bannister described interstellar objects as the only samples we'll ever have from other star systems, at least in our lifetimes. We can't send probes to other stars' distances too vast, travel times too long. Even our fastest spacecraft would take 70,000 years to reach the nearest star system. But interstellar objects come to us. They deliver samples directly to our doorstep free of charge. If only we can study them before they leave. That's the tragedy of interstellar discoveries, they're fleeting. Oumuamua was observable for only weeks before becoming too faint. 2I/Borisov lasted months. 3I/Atlas, maybe 6 weeks of quality observation time before fading into darkness. You get one chance, one shot to point every available telescope at the object, capture spectra, measure brightness, analyze the tail, and squeeze out every possible byte of data before it's gone forever. No do-overs, no return visits. Once it leaves, it's gone for millions of years. So when we talk about the science of interstellar objects, we're really talking about the science of desperation, maximizing information from minimal observation time. Every photon counts, every spectrum is precious, and every discovery raises more questions than answers. Because 3 examples aren't enough to understand the diversity of objects wandering between stars. But those three examples are teaching us that interstellar visitors might be far more common than we imagined. And each one carries secrets about star systems we'll never reach, wrapped in ice and rock, travelling at speeds that would vaporize anything we could build. The universe is delivering messages to our doorstep. The question is, are we paying enough attention to read them? And what can we learn from the messenger that came before 3I/Atlas, the one that sparked the biggest controversy in modern astronomy? October 19th, 2017. The Pan-STARRS telescope in Hawaii detects something unusual streaking through the inner solar system at 196,000 miles per hour. By the time astronomers realise what they're looking at, the object is already leaving, racing back toward interstellar space. They name it Oumuamua Hawaiian for scout or messenger from afar arriving first. And for the next 7 years, this cosmic visitor would spark the most heated scientific controversy since, well, probably ever. Because Oumuamua didn't just challenge our understanding of interstellar objects, it made serious scientists start asking a question they'd spent careers avoiding. Could this be alien technology? Here's how it started. Rob Werrick, a postdoctoral researcher at the University of Hawaii, was reviewing Pan-STARRS data when he noticed an object moving fast, really fast, across multiple image frames. Initial trajectory calculations showed something shocking eccentricity of 1.2. Hyperbolic, unbound to the sun. This was it, the first confirmed interstellar visitor. Astronomers worldwide scrambled to observe it before it disappeared. They had maybe 3 weeks before it became too faint to study. The clock was ticking. Early observations revealed something bizarre about Oumuamua's shape. Its brightness varied dramatically over its roughly 7.3-hour rotation period, changing by a factor of 10 in brightness. That level of variation suggests an object that's extremely elongated, like a cigar or needle. The calculations indicated an aspect ratio of at least 10:1, maybe more. Imagine a cosmic cigar about 400 meters long and only 40 meters wide, tumbling end over end through space. Nothing like that had ever been seen before. Asteroids are usually roughly spherical or maybe 2:1 or 3:1 elongated, but 10:1, that's weird. That's, how did this even form weird? Dr. Karen Meach, who led one of the first major studies, described it in her paper, The Extreme Axis Ratio Makes Oumuamua Unique Among Known Solar System Objects. But here's where scientists made their first mistake. They assumed the brightness variations meant elongated shape. Later analysis suggested it could also be explained by a flat pancake-like disk tumbling through space, still unusual, but less spectacularly so. The media, of course, had already run with mysterious cigar-shaped object, and that image stuck. Even when the science became more uncertain, then came the acceleration anomaly. And this is where things got genuinely strange. As Oumuamua moved away from the sun, astronomers tracking its position noticed something unexpected. It was accelerating. Not much, just a tiny push that didn't match gravitational predictions. When comets do this, it's easy to explain their outgassing, releasing jets of vapour that act like tiny rocket engines, pushing the comet slightly off its predicted path. But Oumuamua showed no visible tail, no coma, no spectroscopic evidence of outgassing. Yet it was accelerating anyway, about 5 times more than could be explained by radiation pressure, the gentle push of sunlight hitting the object. Scientists proposed various explanations. Maybe it was outgassing, but with materials that don't produce visible tails, pure nitrogen ice, perhaps, or hydrogen. Maybe it was a dust bunny structure, so low density that radiation pressure could push it around. Maybe our trajectory calculations were slightly off. All plausible, all boring, all probably correct. Then Avi Loeb stepped into the conversation with a flamethrower. Loeb, chair of Harvard's astronomy department and one of the most respected theoretical astrophysicists alive, published a paper in November 2018 with a title that made his colleagues spit out their coffee. Could solar radiation pressure explain Oumuamua's peculiar acceleration? His conclusion: maybe. If Oumuamua was extremely thin, less than a millimetre thick like a light sail. A light sail being a proposed method of spacecraft propulsion where giant reflective sails catch radiation pressure from stars to accelerate. In other words, alien technology. Loeb didn't say Oumuamua is definitely aliens. He said, we should consider the possibility that it could be artificial. Subtle difference. Scientifically defensible. But the media heard, Harvard professor says mysterious interstellar object might be alien spacecraft, and absolutely lost their minds. Headlines exploded. Talk shows booked him. Netflix started planning documentaries, and the scientific community, they were furious. Dr. Paul Sutter, an astrophysicist at Ohio State, called Loeb's hypothesis lazy sensationalism. Dr. Michael Bannister tweeted, "Extraordinary claims require extraordinary evidence, and we have none." The backlash was swift and brutal, not because Loeb's physics was wrong, the light sail hypothesis is technically possible, but because he jumped to an exotic explanation without exhausting mundane ones first. That's the opposite of how science is supposed to work. You don't start with aliens. You end with aliens only after ruling out everything else. But here's the uncomfortable truth: Loeb wasn't entirely wrong to raise the question. If we ever do encounter alien technology, it'll probably look weird. It'll probably violate our expectations. And if we automatically dismiss anything unusual as natural phenomena without seriously investigating, we might miss the most important discovery in human history. The problem wasn't asking the question. The problem was how the question got amplified by media desperate for clicks, turning legitimate scientific uncertainty into proof of alien visitation. The Oumuamua controversy taught us several painful lessons about scientific communication in the internet age. First, uncertainty gets weaponized. When scientists say we're not sure what this is, the public hears it could be anything, including aliens. Second nuance doesn't survive headlines. Loeb's carefully worded. We should consider artificial origin as one hypothesis. Became Harvard scientist confirms alien spacecraft. Third, once a narrative takes hold, it's almost impossible to correct. Years later, polls show a significant percentage of Americans believe Oumuamua was probably alien technology, despite the scientific consensus that it's almost certainly a natural object with unusual properties. What did we get right? We detected it. We tracked it. We gathered data despite having only weeks before it faded from view. We demonstrated that our survey systems can find interstellar visitors, and we mobilized the global astronomical community quickly. Those are genuine wins. What did we get wrong? We let speculation run wild before exhausting prosaic explanations. We failed to communicate uncertainty effectively to the public. We allowed personalities and ego to overshadow collaborative science. And perhaps most importantly, we revealed that we're not ready institutionally or psychologically for what happens when we find something truly anomalous. Do we investigate rationally, or do we retreat into dogmatic positions, either definitely aliens or definitely not aliens, without doing the hard work of ruling things out systematically? When 3I/Atlas appeared in December 2024, astronomers approached it differently. No wild speculation, no premature exotic hypotheses, just careful, methodical observation and analysis. The metallic signatures in the spectrum interesting, but let's measure them more precisely before drawing conclusions. The slightly offset tail worth noting, but not evidence of anything extraordinary without further data. The unusually high albedo strange? Yes, but strange doesn't mean artificial. We learned from Oumuamua. We learned that caution beats sensationalism. We learned that the public doesn't need aliens to find space exciting real science. Honestly communicated is plenty thrilling. We learned that when you find something weird, the first question isn't, is it aliens? It's what natural processes could explain this, and only after exhausting those possibilities, truly exhausting them, not just getting impatient, you consider more exotic explanations. But Oumuamua also taught us something else. Every interstellar visitor is unique. We can't assume 3 eye will behave like 2 eye, or that future objects will fit patterns we think we understand. Each one is a sample from a different star system, potentially billions of years old, carrying chemical fingerprints of environments we've never seen. And when you only get 3 examples, you can't make assumptions about what's normal versus what's anomalous. So as we study 3/Atlas, we carry the lessons from Oumuamua like scar tissue, painful but instructive. We're more careful with our words, more rigorous with our hypotheses, more aware that every statement will be amplified and potentially distorted. But we're also more excited, because we now know interstellar visitors aren't once-in-a-lifetime events, they're regular occurrences, and each one offers a chance to learn something new about the galaxy beyond our tiny corner of it. The question is, how do these 3 messengers compare, and what patterns, if any, are starting to emerge? 3 interstellar visitors, 3 cosmic messengers from beyond our solar system, 3 chances to understand what's wandering through the galaxy. But here's the fascinating part, they're completely different from each other. If you lined them up side by side, you'd struggle to believe they came from the same category of object. It's like meeting 3 aliens and discovering one looks like a cigar, one looks like a comet, and one looks like a shiny disco ball. So what do these 3 tell us about interstellar space, and more importantly, what patterns can we extract from a sample size of exactly 3? Let's start with 1. Oumuamua, the weird uncle of interstellar objects. Discovered October 2017, moving at 196,000 miles per hour. Eccentricity 1.2. We've already covered the drama, but let's focus on the physical facts. Size approximately 400 meters long, maybe 40 meters wide if the elongated cigar shape is correct, or perhaps 400 by 40 meters if it's pancake-shaped. Either way, aspect ratio around 10:1, extremely unusual, colour reddish, similar to objects in our outer solar system that have been radiation-weathered for billions of years, composition unknown, but spectroscopy showed no significant outgassing despite the acceleration anomaly. Albedo around 0.1, pretty dark, which is normal for most small bodies in space. The defining characteristic of Oumuamua, its mystery. It didn't fit the template. It looked nothing like comets or asteroids we know. Its shape was bizarre. Its acceleration was unexplained. Its origin, traced backward, suggested it might have come from the direction of the star Vega, but that's uncertain because Vega wasn't where it is now when Oumuamua started its journey millions of years ago. We had 3 weeks to study it before it faded from view, and in those 3 weeks we collected more questions than answers. It was tumbling chaotically, rotating every 7.3 hours, reflecting light wildly as different surfaces caught sunlight. And then it was gone, leaving behind a legacy of controversy and a scientific community desperate for a second example to compare it to. Enter 2I/Borisov in August 2019, the normal one, discovered by amateur astronomer Gennady Borisov, moving at roughly 110,000 miles per hour, eccentricity 3.4. And here's what made astronomers breathe a sigh of relief. Borisov looked like a comet, a completely ordinary, unremarkable, boring comet. Nucleus size roughly 0.4 to 1 kilometer in diameter, bigger than Oumuamua. It had a visible tail, a proper coma of gas and dust. outgassing behaviour exactly like comets born in our own solar system. Spectroscopy showed water vapour, carbon monoxide, cyanogen, all the standard comet ingredients, the colour reddish, similar to Oumuamua and solar system comets. Albedo around 0.04, dark as charcoal, completely typical. Composition analysis showed dust-to-gas ratios consistent with comets from the Kuiper belt. One study even measured the ratio of carbon isotopes and found it matched solar system values almost perfectly. In other words, 2I/Borisov was proof that some interstellar objects are just normal comets that got kicked out of their home systems. No mystery, no controversy, no sensational headlines. Just a comet doing comet things, except it came from another star. Borisov's trajectory traced back suggested origins in a binary star system, two stars orbiting each other, where gravitational interactions could easily eject comets. It spent months within observable range, giving astronomers plenty of time to study it thoroughly. Scientists measured its rotation period at roughly 8 hours. They tracked its brightness variations. They watched it develop multiple tail structures as different regions of the nucleus heated up. It was textbook, it was comforting. It suggested that interstellar space is filled with ordinary objects doing ordinary things, just very far from home. Now, 3I/Atlas, the shiny enigma, discovered December 2024 by Gerald Mitchell, moving at 140,000 miles per hour, eccentricity 3.5, size approximately 0.8 kilometers in diameter, similar to Borisov. But here's where it diverges: albedo of 0.6, 60% reflectivity. That's not comet-like. That's not asteroid-like. That's mirror-like. For context, Borisov reflected about 4% of incoming light. 3I/Atlas reflects 60%. That's a 15-fold difference. That's what the hell is this made of territory. The tail is present but offset from the ideal anti-solar direction by about 23 degrees, unusual but not impossible. Spectroscopy shows standard comet materials, water ice, cyanogen, carbon compounds, but also those hints of metallic signatures. Iron oxide absorption features that shouldn't be prominent in a typical comet. Colour slightly bluer than Oumuamua and Borisov, suggesting either a different surface composition or less radiation weathering. Rotation period 7.3 hours, fast enough to potentially affect its shape through centrifugal forces, and that brightness constantly bright enough to suggest either a large cross-section or an unusually reflective surface. What makes 3I/Atlas special, it's the hybrid. It has the tail and outgassing behaviour of Borisov. It has the unusual properties and mystery factor of Oumuamua. It's bright like fresh ice but shows signs of metals. It's acting like a comet while looking like something else. It's the middle child of interstellar objects, taking traits from both older siblings and adding its own twist. So let's compare directly. Speed Oumuamua fastest at 196,000 mph. Then 3I/Atlas at 140,000 m. Then Borisov at 110,000 m. Size Borisov largest at potentially 1 kilometer. Oumuamua and Atlas both around 0.4, 0.8 kilometers. Shape Oumuamua extremely elongated. Borisov and Atlas probably more spherical or irregular. Albedo Atlas brightest at 0.6. Oumuamua medium at 0.1. Borisov darkest at 0.04. Composition Borisov most comet-like. Atlas hybrid with metal hints. Oumuamua completely unknown. Behaviour Borisov and Atlas show normal comet activity. Oumuamua showed mysterious acceleration without visible outgassing. Here's the uncomfortable truth. 3 examples don't make a pattern. You can't draw statistical conclusions from n equals sine 3. Maybe all interstellar objects are wildly different because they come from different star systems with different formation conditions. Maybe we're seeing selection bias, we only detect the unusual ones that pass close and are bright enough to spot. Maybe the normal interstellar objects are too dark, too small, or on trajectories too far away to ever register in our surveys. But if we try to extract patterns anyway because humans can't resist pattern making, here's what tentatively emerges. Interstellar objects seem to move fast, typically 100,000 to 200,000 mph relative to the Sun. They seem to have high eccentricities, well above 1. 0 indicating clear interstellar origin. They come from random directions, no preferred angle or trajectory. Some behave like comets, some don't. Some are bright, some are dark. Some are elongated, some aren't. In other words, there's no pattern. They're diverse. Which probably tells us that planetary systems across the galaxy produce wildly different types of ejected debris. So what can we predict about 4 of the next interstellar visitor based on current detection rates and theoretical models? We should find one every year or two now that our survey systems are better. It'll probably have eccentricity above 1.0 velocity over 100,000 mph, and a trajectory clearly originating from outside the solar system. Beyond that could be anything. Could be dark and rocky like an asteroid. Could be icy and active like a comet. Could be shiny and metallic-ish like 3I/Atlas. Could be shaped like a pancake, a cigar, a sphere, or something we haven't imagined yet. The beauty of interstellar objects is their unpredictability. Each one is a surprise package from a star system we'll never visit, carrying chemical signatures and physical properties shaped by environments completely unlike our own. Some star systems might produce carbon-rich comets, some might eject metal-rich planetesimals, some might send radiation-blasted husks of former moons. We won't know until they arrive. And that's what makes this exciting. We're essentially doing comparative planetology across star systems, using only the debris that happens to wander past. It's like studying global ecosystems by examining 3 pieces of driftwood that washed up on your beach. Limited data, but better than nothing. What we do know, interstellar visitors are more common than we thought. The galaxy is full of wandering objects, ejected from their birth systems, drifting through the void, occasionally passing through another star's neighborhood, and every one that comes close enough to see is a gift, a chance to study materials and processes from star systems light years away. 3 down, infinity to go. And somewhere out there, right now, the object that will become 4I/Atlas is already on its way. The question is, will we be watching when it arrives? 3 interstellar visitors in 7 years. That might sound rare, like winning the lottery 3 times. But here's the reality. Slowly dawning on astronomers, interstellar objects aren't rare at all. We're just really bad at seeing them. And that realization is forcing us to rethink everything we thought we knew about our place in the galaxy. Before 2017, theoretical predictions suggested maybe 1 interstellar detection per decade. Then Oumuamua showed up, then Borisov 2 years later, then Atlas 5 years after that. Either we've been extraordinarily lucky, or the galaxy is far more crowded with wandering debris than anyone predicted. Spoiler, it's the second one. Doctor. Amaya Moro-Martin's 2019 analysis suggested that at any given moment, there could be 10,000 interstellar objects larger than 100 meters within Neptune's orbit. But we can only detect maybe 1% of them. The rest are too far, too small, or too dark. They're passing through right now invisible ghosts carrying stories from distant star systems, and we have no idea they're there. Scale that across the entire solar system, and you're talking potentially millions of interstellar objects at any given time. Not rare, common. We just weren't looking properly. That abundance raises uncomfortable questions for planetary defense. NASA tracks over 30,000 near-Earth objects, asteroids and comets that could potentially hit Earth. But those follow predictable orbits we can calculate years in advance. Interstellar objects. They come from random directions at random times with 0 warning. You can't predict them. You can't track them until they're already here. And if one happened to be on a collision course with Earth, we'd have weeks at best to respond, not years. Before you panic, the odds of an interstellar impact are incredibly low. Space is vast. Earth is tiny. Even with thousands of interstellar objects passing through, the chances of one hitting us are astronomically small, maybe once every several million years. But incredibly unlikely isn't impossible. And the question is, what would we even do? Our current planetary defense strategies assume years of preparation. Deflection missions like NASA's DART experiment, which successfully altered an asteroid's orbit in 2022, require time to launch, intercept, and apply force gradually. You can't do that with weeks of warning. An interstellar object moving at 140,000 miles per hour doesn't give you time for committee meetings. It gives you time to say goodbye. We need faster response systems. We need standing deflection capabilities. We need to take the threat seriously, even if probability is low, because consequences would be catastrophic. But let's shift from destruction to creation, because interstellar objects connect to one of biology's most fascinating theories, Panspermia. That's the hypothesis that life, or at least life's building blocks, can spread between star systems via comets and debris. Sounds like science fiction, but the physics works. Organic molecules are surprisingly hardy. They can survive frozen vacuum for millions of years. Amino acids have been found in meteorites. Complex organic compounds exist in interstellar clouds. The chemistry of life is common in the universe. Here's the scenario: a comet forms in a star system where life exists. Maybe primitive microbes. Maybe just complex organic molecules. That comet gets ejected, travels through interstellar space for millions of years, and eventually crashes into a young planet, say, Earth, 3.8 billion years ago. The impact delivers organic materials that seed life's development. Life on Earth didn't start from scratch. It started from a recipe delivered by Cosmic Courier Service. Sounds wild, but 3I/Atlas and its siblings prove interstellar delivery is real. Objects do travel between star systems. They do carry materials from one place to another. Whether they carry life or just chemistry is still debated, but the mechanism exists. And if it works one way, materials from other systems reaching Earth, it works the other way too. Earth material, blasted into space by asteroid impacts, could be wandering the galaxy right now, carrying our biosphere's chemical signature to distant star systems. We might be both recipients and senders in a galactic exchange program running for billions of years. Now let's talk about actually catching one of these visitors, because that's the dream keeping mission planners awake. Imagine intercepting an interstellar object, matching its velocity, landing on it, and bringing samples back to Earth. You'd have material from another star system, actual physical samples without travelling light years. The scientific value would be immeasurable. We could analyse isotope ratios to determine the parent star's age and composition. We could study organic molecules to see if they differ from solar system chemistry. We could answer fundamental questions about planetary formation across different stellar environments. The problem? These things are moving insanely fast and they are only nearby for weeks. NASA's Comet Interceptor mission, scheduled for 2029 launch, is designed to sit in space waiting for a suitable target, possibly an interstellar visitor, then rapidly maneuver to intercept it. NASA has proposed similar concept spacecraft pre-positioned in orbit, ready to launch when an interstellar object passes through. You can't launch from Earth fast enough by the time you design the mission, build a spacecraft, and launch. The target is gone. You need to be ready and waiting. The technology exists. We have ion drives capable of high delta-V maneuvers. We have autonomous navigation. We have instruments that can analyze composition, measure temperature, capture images. What we need is funding, political will, and luck to catch the right object at the right time. But it's doable. Within the next 20 years, we could realistically sample an interstellar visitor. And when we do, it'll be one of humanity's greatest achievements, touching material from another star without leaving our solar system. Beyond science and technology, interstellar objects force a philosophical shift. For most of human history, we've thought of the solar system as isolated, our 8 planets, their moons, some asteroids and comets, all bound to our sun, separate from the rest of the galaxy, a closed system, a cosmic island. But interstellar visitors prove that's wrong. We're not isolated. We're part of a galactic ecosystem where material constantly moves between star systems. Objects enter, objects leave. We exchange chemistry with the rest of the Milky Way. We're connected to distant stars in ways we're only beginning to understand. That changes the Drake equation, the famous formula estimating the number of communicative civilizations in the galaxy. Traditionally, it treats star systems as isolated, asking what's the probability that life develops, intelligence evolves, technology emerges on any given planet. But if material regularly moves between systems, you have to factor in cross-contamination. The probability of life arising might be higher because chemistry gets shared. Or conversely, life's rarity might make interstellar panspermia our best hope for finding biology beyond Earth, not independent origins, but spread from rare sources. Either way, common interstellar traffic forces us to think bigger. We're not alone in the void. We're part of a network, a galactic community connected by wandering debris, travelling for millions of years, carrying messages written in chemistry and physics. Some messages we're learning to read. Others will take decades to decipher. And some we might never understand because we lack the context. The bigger picture is this. 3I/Atlas isn't just an interesting discovery. It's evidence that our solar system is permeable. The galaxy is interconnected, and the universe constantly delivers opportunities if we're paying attention. 3 interstellar visitors in 7 years means we're entering a new era, comparative stellar system science, where we study other star systems not by visiting them, but by analysing the debris they send our way. The question now isn't whether more interstellar visitors will come. They will. They're probably passing through right now. The question is, what will we do with the opportunities they provide? Will we simply catalogue them and watch them leave? Or will we take the next step, catching one, studying it, learning everything we can before they disappear back into darkness? Because the universe is offering us a chance to explore beyond our solar system without ever leaving it. And anyone with a telescope can help make it happen, starting with you. You've learned about Gerald Mitchell, a high school teacher who discovered an interstellar visitor from his backyard. You've seen how amateurs confirmed 3I/Atlas faster than billion-dollar institutions. Now comes the most important question. What's your role in this? Because this isn't a story that happens to other people. This is a story you can be part of tonight. Let's start with the easiest entry citizen science projects you can join right now without spending $1. Zooniverse hosts dozens of astronomy projects where volunteers analyse real data. Planet Hunters examines telescope data looking for exoplanets. Backyard Worlds. Planet 9 has volunteers scanning infrared images for brown dwarfs and the hypothetical 9th planet. Galaxy Zoo lets you classify galaxy shapes, training AI systems. These aren't busy work. Your classifications contribute to published papers. You get credited. Your pattern recognition matters because human brains spot anomalies that algorithms miss. Asteroid Tracker helps identify and track near-Earth objects. Globe at Night measures light pollution by counting visible stars, simple but crucial. Radio Jove teaches you to detect Jupiter's radio emissions using homemade antennas. These projects require nothing but time, curiosity, and internet connection. You could be contributing to space science right now, but maybe you want your own telescope, your own chance to be the next Gerald Mitchell. Here's the truth: you don't need $6,000 to start. Begin with binoculars. Good 10x50 models will show Jupiter's moons, Saturn's rings, star clusters, nebulae. That's $100 to $300, not enough to discover interstellar objects, but enough to fall in love with the sky and learn what you're looking at. Ready to upgrade a beginner telescope like Celestron NexStar 4SE or Orion Starblast costs $500 to $800. Computerized mounts find objects automatically, no expert navigation needed. Add a basic camera's OSI 224MC runs about $300 and you can start imaging. Not discovery level yet, but learning images. You'll understand how sensors work, how exposure times matter, how atmospheric conditions affect results. Serious about contributing to real research. You're looking at $2,000 to $5,000 for survey-capable equipment, an 8-inch or 11-inch Schmidt Cassegrain telescope on a computerized equatorial mount, a cooled CCD camera with low noise, software for image capture, calibration, and astrometry. That's Gerald Mitchell's setup. Not cheap, but compare it to golf clubs or photography gear, it's competitive. Plus, you might discover something that gets your name in textbooks. Can golf clubs do that? The astronomy community is absurdly welcoming. Join Cloudy Nights forums, our astrophotography subreddit, or Discord servers like the Astro Imaging channel. Post your first terrible image and you'll get detailed advice. Not mockery. Try these settings. Your focus is off. Here's how to fix it. Everyone remembers being terrible at first. Everyone wants to help because more observers means more discoveries. Local astronomy clubs exist in almost every city. They hold star parties where members share telescope views with anyone who shows up. Google your city astronomy club and you'll find one. Show up. Ask questions. Experienced astronomers love sharing their passion. They'll guide you from complete beginner to competent observer faster than you'd learn alone. Now, let's say you actually find something. You're imaging a patch of sky and there's an object that moved between frames. What do you do first? Don't assume it's interstellar. It's probably a satellite, asteroid, or known comet, but it might not be. Here's the protocol capture. At least 4 images spanning 30 minutes to an hour. Measure the object's position in each frame using free software like Astrometrica or AstroImage-J. Calculate angular velocity, how fast it's moving across the sky. Check against known databases, the Minor Planet Center's database or NASA's JPL Small Body database. If it's catalogued, you've independently confirmed a known object. Still valuable data. If it's not in any database, now it gets exciting. Post observations to the Minor Planet mailing list monitored by astronomers worldwide. Include images, measurements, equipment specs, observation time. Be precise. Be honest about uncertainty. Within hours, other observers will try to confirm. If multiple independent confirmations come in, the Minor Planet Center calculates a preliminary orbit. If that orbit suggests something unusual like interstellar trajectory, you've just made history. And yes, you get credit. The object might be named after you. Want inspiration? David Levy, co-discoverer of comet Shoemaker-Levy 9 that crashed into Jupiter in 1994, is a college dropout who discovered his first comet using homemade equipment. He's found 23 comets total. Terry Lovejoy, an IT manager from Australia, discovered 6 comets using telephoto lenses on camera tripods simpler than most amateur gear. One became bright enough to see with the naked eye. Masayuki Iwamoto from Japan discovered his first comet in 2018 using a digital camera and 150mm telephoto lens. Total equipment cost under $1,000. International headlines followed. He's an amateur with a day job who decided to look at the sky more carefully than most people bother. These aren't freaks of nature with superhuman abilities. They're people like you who got curious. bought equipment, learned skills, and put in the hours matter. Levy discovered 23 comets over decades of searching. Lovejoy spent years imaging before finding his first. Gerald Mitchell imaged for 11 years before 3I/Atlas appeared. Persistence is the secret. Keep looking, keep imaging, keep analysing. The universe rewards patience. Here's my challenge, the next interstellar visitor 4. 5I. 6, I could be found by you. Not by NASA, not by a billion-dollar observatory. By you, in your backyard, with equipment you saved on a random Tuesday when you decided to point your telescope at empty-looking sky. Because that's how 3I/Atlas was found. That's how 2I/Borisov was found. That's how discoveries happen now. The sky isn't reserved for professionals anymore. It belongs to anyone willing to look up and pay attention. Right now, objects are passing through our solar system that nobody knows about. Interstellar visitors carrying stories from distant star systems. Comets making their first pass through the inner solar system in millions of years. Asteroids on uncalculated trajectories. They're up there, waiting, moving, and they don't care whether you have a PhD or a high school diploma. They only care whether you're watching. So go outside tonight. Look up. Find a dark spot away from city lights if you can. Let your eyes adjust for 10 minutes and just watch. See how many stars appear that you didn't notice at first. Watch for satellites crossing silently. Spot a planet Venus, Jupiter, Mars, Saturn. Download a star map app and learn a few constellations. That's step 1. That's where Gerald Mitchell started. That's where everyone starts. Maybe you'll catch the bug. Maybe you'll start wondering what else is up there. Maybe you'll buy binoculars, then a telescope, then a camera. Maybe you'll join a club, learn astrometry, start imaging. Maybe 5 years from now, you'll be posting to the Minor Planet mailing list with images of something nobody's ever seen. Maybe your name will be attached to the 4th confirmed interstellar visitor. Because someone will find it. It's just a question of who's looking when it arrives. The universe is offering you an invitation. Here's a mystery. Here's a frontier. Here are tools that let ordinary people explore extraordinary things. Are you interested? If your answer is yes, even a tentative, curious yes, then you're already part of this story. You're already one of us. Welcome to the community of people who refuse to believe the sky has given up all its secrets. We've got telescopes, forums, data, and endless questions. And somewhere out there, right now, an interstellar messenger is on its way. Will you be the one watching when it arrives? Keep looking up. The next discovery could be yours,